Okay, welcome. This is week 7. We're now past the halfway point. So we're lights at the end of the tunnel. And today is actually a really important week, an important webinar in terms of what we're going to be doing. Pretty much everything we're going to do for the rest of this entire course uses what we're doing today. And as always, I'll start out with Q&A if you have any. And then after that, we'll talk about the null hypothesis and the alternative hypothesis. Really important. It's a big piece of statistics. And so we're going to be looking at what's called a hypothesis test. And that's what chapter 9 is all about. It's all about hypothesis testing, which is really making a scientific decision. So the idea is, you think, maybe something's true, but you want to show statistically that it's true. Okay, that there's a very strong chance of it being true using statistics. And that is a big deal for many, many, many things that we do. So I'm going to kind of walk you through the steps on hypothesis testing. And to let you know, hypothesis testing we're moving into chapter 9. It's also in chapter 10. It's also in chapter 11. It's also in chapter 12. It's also in chapter 13. So it's really important that you get this stuff down because everything we do for the last half of the entire course uses the hypothesis testing for every chapter. So we'll start out with the very first step, and that is decide on the null hypothesis and alternative hypothesis. Then we'll say, well, what are the errors? What bad things can happen if you end up with an error? And there's 2 errors, and one is called a type 1 error. The other is called a type 2 error. Then we'll get into what's called the level of significance. It's kind of like, how okay are you with being wrong? No, you can't be right 100% of the time. But the question is, what percent of the time are you okay with being wrong? And we'll talk about that. And that's called the level of significance. We'll talk about how you make decisions of the level of significance on choosing it. Then we'll get into what's called the p-value. Okay, so the p-value is kind of like, it's a measure of rarity. The idea is that how rare would it be for this to happen if you were wrong in the first place? And that's going to be the p-value, and it's a probability. P stands for probability, by the way. Then we'll talk about how do you state your conclusion. So you collect your data, you run your statistics, you find the p-value, and then you have to make a conclusion. And what is the verbiage to make a conclusion for a hypothesis test? And then we'll talk about interpreting the p-value. Okay, and by the way, this week has a lot of writing. Just let you know, there's a lot of writing, a lot of sentences going on. And there's a conclusion, there's a p-value, and there's interpreting the level of significance. Also has a lot of sentences. So expect to do a lot of writing, and I'll give you templates that will help you on what language you are required to have in the writing. And I want to let you know, I'm not trying to be mean. I'm trying to make it easier to see a template, but I also require you to use a template. And there's lots of reasons. One is, again, it makes it easy. That way you can be scientifically, statistically sound.
A tablet.
You know that you're doing it right. And I want to let you know, if you don't use the verbiage that I tell you to use, I take off points. Okay. AI won't use the verbiage, so don't use AI to answer your question, or I will take lots of points off. So don't even think about it. Make sure you understand what we're doing in our webinar and use those templates to answer the questions. Okay, and they're going to be used again in this week's stuff. They're also going to be used on your exams for all the rest of the exams. They're also going to be used on the project. So these templates are going to be real helpful. And then finally, we can start talking about Project 2. We were not completely ready to go through all the details of Project 2 because Project 2 mostly focuses on Chapter 10, and that's next week. But the two main things that Project 2 does are confidence intervals and hypothesis testing. So we're going to be talking about hypothesis testing this week. And last week we did confidence intervals, so it's time to start thinking about it. It turns out Chapter 10 is all about comparison studies, and that's not what we're doing this week. So you're not quite ready to get all the details yet, but I'd like to give you a heads up or how to plan on the project and think about it. So are there any questions? Are there any questions about anything from the class?
I used it.
Question? I think you're talking to someone else. Any questions about anything from the class? If you don't have any now, but you end up with questions, that you come up with halfway through today, then please feel comfortable asking, because that's one of the big points is for me to be able to answer questions when you have them. And, it's immediate answer instead of sometimes you have to wait hours or before you get an answer if you post on the Q&A board or something. And this way you get an immediate answer. So it is important that you ask questions if you have them. Okay, it turns out this hypothesis stuff that we're doing, you actually learn about this in middle school. You learn about this in middle school, but some of you might have been a while since you've been in middle school, but we'll be talking about it. And the idea is, and let me go into the hypothesis testing, and I want to give you an example. And to me, this is like the most important, somewhat recent example, in the last 5 years or so of any hypothesis test that's been done. So I bring this up more than once. And in fact, what we're doing today is exactly what they did. Next week, you'll know more and you'll be able to see more of what they're doing, almost exactly. And that is, let's consider you are part of the FDA, Federal Drug Administration. And, go back in time a few years back. And Pfizer or Moderna, you get to choose because it was almost the same time, have said that we have this vaccination and it works and it's wonderful. So the FDA, are they just going to say, oh, we trust you, it's wonderful? Is that what happens? Yeah, that's not what happens. That's not what happens. If that were to happen, then you could have sometimes, millions of people dying of something that doesn't work at all. So that's not what the FDA does. Okay, what the FDA does is it requires or sometimes it conducts their own hypothesis test to see if this drug actually works. So that's what happened in terms of COVID vaccination. And since COVID vaccination is, COVID unfortunately is still around. One of my colleagues just got it again. It's a bummer, but part of it. But the question is, can we trust whether this vaccination works or not? And that's a big deal. Okay, I don't trust just a company saying it works because they want to make money. But I do trust the FDA. They're not into making a profit. They're into checking and statistically and scientifically analyzing to see if it is actually working. Very different than a company that's making a vaccination. So what they did is they did a hypothesis test. So there's step-by-step process on doing a hypothesis test. The first step is to state what's called the null and alternative hypotheses. So when it was happening, this was a long time ago, this was in, I think it was in 2020, towards the end of 2020, when they were doing the test. And about 4% of all people were getting COVID in, I don't remember how many months, but let's just say over a couple months time. Okay. Okay, COVID, most people weren't getting COVID in those days. I don't know if you remember, but some people did. And when they got it, it was really bad. There was no vaccination, especially if you're older. If you're older, you probably died, you know, or not probably, but there was a big percent that died. So what the null hypothesis is that what Pfizer or Moderna is saying is not true. This vaccination doesn't help at all. So if the vaccination doesn't help, then what you would say is the population proportion of anyone who could get vaccinated, the proportion of them getting COVID is still going to be 4%. Does that make sense? Okay. Yeah, people didn't have pronounced symptoms, but I think they still had a test to find out if you had it, even if you didn't have symptoms. So they could at least do that. Yeah, this isn't how many people died. This is how many people got COVID at the time. Okay. So the idea is that if it's still equal to 4%, the vaccination is completely useless. Does that make sense? Because if it was 4%, you get the vaccination and you still got a 4% chance of getting it, then they wouldn't accept it. On the other hand, what the drug companies were saying is that our vaccinations works. Not 100% effective, but it makes a big difference if you get the vaccination, that you are less likely to get COVID. And the way you state that statistically is that for the population who get vaccinated, the population proportion of all of those who got vaccinated who end up with COVID is going to be less than 4%. So it actually reduces the percent chance of getting COVID.
Okay, geared up then.
Any questions on that idea? In symbols, you write for the null hypothesis, we always write this right here.
Okay.
So it's important. I would recommend writing it down on a piece of paper so you get used to it, because it's going to happen for the rest of this entire course.
Let me pull my pants on and then I'll.
And that is H, and there's a subscript 0. Okay, and as I was mentioning earlier before I started the video, the British got to it before the Americans, and the way they say 0 is not. So we usually call it H naught because we use the British way of saying 0. Okay. So H naught, and then there's a colon. This is not an equal sign. Do not write H naught equals. It's H naught colon. Okay. And so the null hypothesis is not that 4% don't get it. It's that 4% still get it. Do you see how that works? So P is a population proportion. So the population proportion of the population who got vaccinated, the population proportion of those who get COVID is still 4% or 0.04. And you write P equals 0.04. Yeah, they did have a large sample size. I'll get that in a minute, but let me finish writing down, talking about H naught and H1, and then we'll talk about the sample size. Okay. H1, and by the way, it turns out everybody writes H naught. Every book, every statistic, they all write H naught. Okay. Sometimes we'll write the null hypothesis, but it's a lot quicker to write H naught, and that's what you're going to usually see. Not everyone writes H1. It turns out there's 2 ways of writing it. Sometimes they'll write H1. I personally like H1 because it's the number after 0 is 1. Makes sense? But the other way of writing it, sometimes you'll see HA. They'll use an A because that's the first letter of alternative hypothesis. So don't be surprised if you see in other sources H sub A instead of H naught. And then always colon. And then P, the population proportion of all of those who got the shot, who end up getting COVID, is less than 4%.
We're starting here.
About 5 miles.
Any questions? Any questions on on the null hypothesis and the alternative hypothesis. Okay, I want to give you a heads up about this. In our class so far, we've had two types of survey questions. One is the yes/no survey question, and that's where we use P for proportion. What's the other kind of survey question besides the yes/no survey question that we've had that we've dealt with for confidence intervals? What's the other kind? Yeah, that's when you had a survey question that was quantitative, and then it's not the proportion that matters, it's the mean. Okay, if it's the mean, do not use the letter P. What letter do you think we use for mean? We've seen it many times in this class. Mu. X is for the sample mean, mu is for the population mean, and the hypothesis is always about the population, never about the sample. Got it? So it's very important you get the notation correct. So we're going to say if it happened to be a mean instead of proportion, you'd use a mu instead of a P. X bar is for the sample mean. Exactly. So we don't use X bar in H naught and H1, we use mu if it's quantitative. So that's why I'm saying don't use X or X bar. Use mu if it is for a population mean, with means quantitative survey question. With the yes/no question, it's always a P. Don't get them wrong, because I do take off points if you use the wrong letter. Got it? If you don't want to find how to do mu on your computer, you can always do mu. P, I hope you all know how to type P in a computer, but that's easy to find. Okay, sound good so far? Okay, so there was a question about how many did they survey? It turned out they did a survey of 50,000 people. Oh, sorry, 40,000 people, not 50, 40,000 people. Sorry if I said it wrong. So 40,000 people. And it turned out the way they did it was something, they used a randomized control study. We'll talk about that in chapter 10. But you need a big study when it's a yes/no survey question, when you have a very small % chance of saying yes. And saying yes means I got COVID. You don't want to say yes, but hopefully you're honest. And actually what they did is they did a test on everyone. Okay, so that's why they needed a very large sample size. When you have a small number like 0.04, it turns out you need a much larger sample size. Okay, for a couple reasons. One is NP and NQ will be really small. So if you let N be 100, that sounds big, then NP is only 4, and that's not bigger than 5.
You're right.
So already you couldn't do it. So that's just a note that the sample size needs to be big when you're doing a survey when our what's called P naught, which is this number we call P naught, is small.
That makes no sense.
Any questions so far? Okay, so now it turns out there are two errors that we want to look at. And you want to look at the errors, you want to look at these potential errors before you do your study. So I want to let you know this is a very, very much ordered list of things you have to do, and it's ordered by time. So the very first thing you have to do is decide what your hypotheses are. What is it you're studying? Okay, and that's going to come from whatever the situation you're looking at was. So for the FDA, they wanted to see whether the vaccination, that people who got the vaccination had a smaller % chance of getting COVID. So there's your H naught and H1. H naught is the same chance, H1 is a smaller chance. Do you see how that works? Okay. The next step is to decide what the type 1 and type 2 ramifications are. So let me give you the definition first. Type 1 error means that you reject the null hypothesis when the null hypothesis is true. Okay? So if you reject the null hypothesis, that means the FDA is going to say that it's not true that P equals 0.04. And it is true that P is less than 0.04. So it turns out rejecting the null hypothesis, the next step is you conclude that the alternative hypothesis is true. Okay? So that means they concluded that P is less than 0.04, but the null hypothesis was true, P was equal to 0.04. Would that be bad, by the way, in this situation with the COVID vaccination? What would happen? Any thoughts? Okay, not as bad as having a vaccination?
As not having.
Huh? Yeah, that would mean that they FDA approves the vaccination and it doesn't work. Okay? So let me give you the ramifications of a type 1 error. So that means the vaccination gets approved, but it doesn't work. So people have to go through the vaccination process. Okay. I don't know if you remember that it was actually a requirement for some places for you to be vaccinated, like to go to a restaurant and other things like that. Okay. And one thing, I don't know about you all, but I've been vaccinated and I've been boosted many times. Because I look at the statistics, by the way. So that would mean that one thing is, boy, I was so tired and exhausted. I didn't die or anything, but it was miserable the next day. So I went through a day of exhaustion. I didn't get out of bed. I was able to think well, but I could hardly move. Okay. So that means one thing is that you have that miserable next day. The other thing is that the other thing I did personally, I'm going to give my personal what I did, is that because I got vaccinated, I was confident that I was much less likely to get COVID. And in particular, that means I wouldn't give it to other people either. And that means one of the things I did is I went and did a family trip. You know, I went and saw my family. I went from, the family all over California. So I did a long, big California trip and got to see everybody. Sounds wonderful, except I did that because I felt like it was much smaller chance of getting COVID. But if it turned out I had a type 1 error, or they had a type 1 error, that means I didn't have a smaller chance of getting COVID. So I went through this misery the next day, and there's a high chance, or decent chance, that I would actually get it and maybe give it to my whole family. And to me, that is, I don't want to hurt my family. Hopefully you don't want to hurt your family either. But so that would have been terrible if it was a type 1 error. Do you see that? It would have been bad. Okay. Any questions on the ramifications of a type 1 error? And something I want to make a highlight of, because I've learned from teaching a long time, a lot of students don't know what the word ramification means. That's not a statistics word, that's an English word. It kind of in simpler terms, it means the bad stuff that happens because you did this. That's ramification. Okay, yeah, the consequences. Okay, the bad consequences. Exactly. So often on exams I could ask, what are the ramifications of a type 1 error? And that's what I'm asking for. Is what are the bad things that would happen? Okay. Yeah, so but with the type 1 error, it's always bad, never good. It's error. So don't even write good things. Errors are bad. Just let you know. Any questions on this type 1 error? Any questions? Okay, so then there's another kind of error. So there's one error, and that is that FDA decided to approve the vaccination when it didn't work. Okay, that means they were able to reject H0, accept that P is less than 0.04 when you have the vaccination, but it isn't. What's the other error that could happen? Any thoughts? Besides saying, hey, it works when it doesn't. What's the other possibility that could happen before you start the test when you're thinking about it? Yeah, that means the vaccination works, but Pfizer doesn't approve it. Okay, so that's called a type 2 error. And what that means is there's not enough evidence to reject the null hypothesis. Okay, and that means another way of saying there's not enough evidence to reject the null hypothesis is we fail to reject the null hypothesis. Often that's how you say it, fail to reject. But the null hypothesis was false, which means the alternative hypothesis was true, but they weren't able to get that data to show that it was true. Okay, and again, it's an error. Errors are bad. What are the ramifications of a type 2 error? Very different than a type 1 error. What are the ramifications of a type 2 error? See if you can put in the chat box or say it. What terrible things happen because of a type 2 error? Yeah, they lose access to a functional vaccine. Yeah, it means that the vaccine doesn't get approved. So nobody gets vaccinated, even though this vaccine works. So you end up not be able to get our country to get vaccinated. We have the COVID nightmare when the vaccination actually worked. Okay, so that's horrible because now all these people are getting COVID when they could have been vaccinated and maybe been much less likely to get COVID. Does that make sense? So it's a very different than a type 1 error. Okay. Yeah, so what's worse? I think a type 2 error is worse in this case. But a little bit, they're both pretty terrible. But if we ended up not having any vaccination and COVID just kept spreading and killing people, then I think a lot more people would have died with a type 2 error than with a type 1 error. Okay. And that, just to let you know, this type 1 error and type 2 error on which is worse, that is one of the judgmental kind of things. It's not like a mathematical formula for saying what's worse. Does that make sense? So in terms of my grading, when I'm looking at your tests, your exams, and your discussion posts, what you have to do is you have to explain why it's worse. And if you have a good explanation of why it's worse, I accept it. Okay? But that explanation, of course, what it is, what the ramifications are, they have to be, right in terms of what the definition of a type 1 and type 2 error. But in terms of what you feel is worse, that's a whole different thing. Does that make sense to everyone? Any questions on that? Okay, and sometimes it depends on who it is, who it's worse for. For example, a type 2 error is definitely worse for Pfizer and Moderna, right? Because they're losing money. See how that works? Okay, so, it depends on who it's for also. And there's just one example. There's many, many, many examples of hypothesis testing. But I like this one because hopefully you're all aware of COVID. I think there's no one that doesn't have a clue anymore. Okay. One of my favorite things is before anyone was even talking about COVID, I actually gave a lecture on the how fast diseases spread when you have a terrible disease, and the next day is when it came out in the news. I was like so proud of that. Okay, and I didn't even know about COVID. I just got lucky. Okay, so the ramification of the type 2 error is that vaccination does not get approved, but it really does work. Nobody gets vaccinated, and 1 million more people still die of COVID. That's terrible. All right, so step 1 was to decide on the null hypothesis and alternative hypothesis. Step 2 is to look at the ramifications of a type 1 and type 2 error. Any questions on step 2? Step 3 is we're going to decide on the level of significance. So the level of significance, it's kind of it's the complement of the confidence level. Do you remember what the confidence level was? That was last week. Hadn't been that long. What was it? What was the confidence level? The level of confidence that we have that we're correct, exactly. It was a probability that the population mean or proportion is within the confidence interval if you're in the business of making confidence intervals. If you make many confidence intervals, that's for each one, that's your probability of the population proportion being in there. It's kind of like the probability of being right. Okay. It turns out, and don't shoot the messenger on this one, I just show you what everyone does. When we're talking about hypothesis tests, we actually think the opposite. Instead of you think about the percent chance of being right, for some reason for hypothesis tests, everyone thinks about the percent chance of being wrong. So the level of significance is the probability of a type 1 error. Okay? Which means that you rejected the null hypothesis and you shouldn't have. Okay? And I will let you know that in our class, we're only going to use 3 different types, and that is 1%, 0.01, 5%, 0.05, and 10%, 0.10. Okay, so that'll be our standard for our class. Sound good? Okay, it's very rare to see anything that is different than these numbers. Okay, occasionally you'll see something less than 0.01. And that's if you have a type 1 error, you end up like killing a whole lot of people. But if the alternative hypothesis was correct, then nothing important happens. Does that make sense? And then you probably want a really small type 1 error. Okay, so most null hypotheses are difficult to prove false. Well, difficult means that you have to do a survey. Surveys are hard to do. You did project 1. That took a lot of work, right? So, and I want to mention another thing is never use the word prove for confidence intervals or hypothesis testing. Basically, for the entire rest of this course, do not ever write that word prove, because you never prove anything. You're confident about it happening. Proof means you're 100% certain. Does that make sense? So you never prove that it's false. Okay, the only way to prove it's false would be to actually do a census of every single person in the entire world. And that's like pretty impossible. Does that make sense? Yeah, so statistically significant evidence, we'll get to that in a bit, but I want to get there. Again, we're going through things in order. All right, so it turns out that the level of significance is the probability of a type 1 error. So if the type 1 error has really bad ramifications, then you want that level of significance to be small, like 0.01. Do you see? If the type 1 error is not so bad, then maybe 0.1. Do you see how that works? But I want to let you know it's a give or take. If you make the level of significance to be really small, so that means the probability of a type 1 error is small, then that is going to result in the probability of a type 2 error being larger. Do you see how that works? So it's a give and take. Because you say, well, maybe I'll make my type 1 error 0.00001. Sounds good. Because that was such a small chance. But then you have a really big chance of a type 2 error. So it's a give and take. It's kind of like with confidence intervals. If you want a really high level of confidence, then you end up with a very wide margin of error. And that's not good. That was give and take for confidence intervals. For hypothesis testing, it's give and take on the type 1 error versus the type 2 error. Okay? So if the type 2 error is worse than the type 1 error, then you're going to use 0.1. If the type 2 error, if the type 1 error is worse than the type 2 error, use 0.01. If they're kind of equally bad, then we use 0.05. I will let you know that if it's like more of a psychology research thing where, or news article where no one's dying or anything, either way, 0.05 is a standard. So 5% is a standard level of significance. So you start at 0.05 and then see, is there a reason I should go up to 0.1 or down to 0.01? Any questions on that? So I'm going to ask you on the exam to explain why you arrived at your level of significance. And you need to talk about which is worse, a type 1 or type 2 error. That needs to be the reasoning. Any questions on the level of significance, the choice for it? Okay, very important that we're doing things in this order. Okay, what do you think the next thing to do is? And the hint is, in the real world, this is the hardest thing. Because what we just did might take 15 minutes, maybe an hour of work. What do you think the hardest thing usually is to do? That could take months sometimes decades. Yeah, the next thing you do is conduct a survey. And I'll answer your question. You asked, can you reduce both of them with a larger sample? And the answer is yes. So the larger the sample size, the smaller chance of error. And we had that with the large numbers. Because if you have a large sample size, then it's very, very likely that the truth will appear. Does that make sense? So that means errors probably won't happen. But why didn't they survey? Why didn't they do a test on 1 million people? Why didn't they do a large sample size with 1 million people? Yeah, there's two reasons, actually. One is it would take too much time. It might take 2 years to do, and then by then you can have 1 million more people dying. Another is it's too expensive. Okay, and that's a big deal. There's actually another one for this particular example. The risk factor is too high. Because there's another thing that could happen when you get the shot if you don't know about it and you haven't tested it in anyone but rats. Do you know what the other thing that could happen? Much worse than too much time or too expensive? It could kill people. When you have a new vaccination and you haven't tried it on people yet, it could end up killing people and have some terrible side effect or, you know, or similar to kill people. So there are lots of reasons why they didn't do more than that. So you want to have just above it, above the amount so that you have a, you know, very good chance of not having a type 1 or 2 error, but not so many that you're going to end up having big risks, expense, and time consumption. So again, that's a long thing that we can't get into all the details in this class. That's more graduate level probably. Any questions on that? So the next step is they collect the data. Okay, and again, that took months because what they needed to do is they needed to get volunteers. Okay, and then they needed to give the volunteers the vaccination. Turns out they did a control study where they randomized half the people got the vaccination, the other half did not get the vaccination, but everyone thought they got the vaccination. Any of you been in a control study like that? Okay, it turns out when I was a college student, I was a very poor college student. There was a message on the college newspaper at UC San Diego that said, if you have the runs, run to the hospital and we'll give you money. if you can be part of our study. And as you might guess, I had the runs that day. And I did it. And it turns out the bad news for me is that I was one of the control people who had a placebo. So actually, I didn't get anything, and it lasted longer than it should have. It sucked. But then they told me a couple days later, all right, come on in and we'll give you some real medicine. So I've been part of it. Okay. Okay. Sugar pill, no, actually, it was a shot. I think it was a shot, if I remember right. It was so long ago, I don't remember. But I do remember being the control state. So I've actually been part of it, as a student, not as a statistician. Okay. So then once you've collected your data, and again, that could take months. This COVID thing took months to do. Then you put the data into the computer and you calculate the p-value. Okay. So I have a picture, and this is something that we've already talked about, and that is if you have a large enough sample size, then the distribution, the sampling distribution, will be approximately normal. Okay? And we're going to make the assumption that H naught is true. So that means we're going to put 0.04 in the middle, or the mean, for the distribution. That's part of the central limit theorem. Okay? Now, what they ended up getting was 0.01. Only 1% of the people that got vaccinated got COVID instead of 4%. By the way, is that good? Can normal be concave? Normal always has this shape. I don't get into the mathematics behind it because it's too hard. It's an e to the negative x squared curve, if that helps. But I don't go into that. Too hard math. So come to office hours if you really want to hear math, then I'll torture you with math. Just let you know. But it has a shape. I want you to know the shape in just general, what it looks like. And the p-value turned out to be 0.004. Okay. Okay. So again, 1% got it, but you want it 1% of the population of the sample got COVID. Okay. When you would expect 4%, but you want to do more than that. You want to say, well, maybe that was just, kind of an occurrence that could happen. How unlikely would it be for 1% of the population, or 1% or fewer of the population, to get COVID if the shot does nothing for you? And that's what the p-value is. It's the probability that if the shot does nothing for you, in other words, if H naught is true, that you'll have something smaller than what you got. In our case, since we have what's called a left-tailed test, which means we're hoping that you have a smaller chance of getting COVID if you get the shot. Any questions on that? Okay, now 0.004 is actually much smaller than 0.1. So it turns out that if you are making a decision, you're doing a hypothesis test, what you're hoping for is to have a p-value less than the level of significance. Because if you have a p-value less than the level of significance, then you say, I get to reject the null hypothesis. Okay, in our class, and this is pretty standard, so I'm going to use it a lot. If p is less than 0.01, we call it strong statistically significant evidence. If p is between 0.01 and 0.05, then we just say there is statistically significant evidence. And if p is between 0.05 and 0.1, then we say there's weak statistically significant evidence. If p is greater than 0.1, then there's no statistically significant evidence at all. So that's some of the language you'll hear a lot. Okay? So what we can say is there's strong statistically significant evidence, okay, to conclude that the population proportion, and I want to let you know, just like confidence intervals, in making your conclusion, you must specifically refer to the population. It's not about the sample proportion. It's the population proportion of all vaccinated people who get COVID is less than 0.04. Any questions? Any questions on what's called the conclusion for the hypothesis test? Okay, by the way, the template I'll get to in a minute. So this is kind of a template, but this is an example. Template, I'm gonna put XXX in where where you don't know yet. Okay, does that make sense? So this is an example that uses a template. Okay, had the p-value instead of been 0.04, been, let's say, 0.15, how would this change? Not much, actually, but the wording, what words would change? Any thoughts? Turns out you get rid of the word strong, and then one other thing changes. No, 0.15 is not weak. Weak is between 5% and 10%. So if it was 15%, you're not even weak. So what you do is, see this significant? What's the opposite of significant? What's the opposite of significant? Insignificant. You put IN. So if the p-value had been large, you put IN. It isn't, so I'm going to erase that IN. So you don't have to change much, actually. It's not strong, by the way. So you would just say there is statistically insignificant evidence to conclude that the population proportion of vaccinated people who get COVID is less than 0.04. Okay. By the way, what do you think the FDA did after finding this out? This is real. Yep, they approved the vaccination. Okay, it's a big deal. This isn't some little thing. This is a big national thing. Do you agree this is like one of the most important hypothesis tests that's happened in the last 5 years? Okay, it's a biggie. Okay, now let's interpret the p-value. So here's the wording for interpreting the p-value. If the population proportion of all vaccinated people who get COVID is 0.04, 4%, and if another study of 25,000 people were vaccinated, okay, in the study they actually vaccinated 25,000, is the way it worked. That was the sample size. And COVID tested during and at the end of the testing time, because that's what they did, then there would be a 0.4% probability. Our p-value is 0.004. If you move the decimal places 2 places, that's 0.4%. So there'd be a 0.4% probability that fewer than 1%, because that right here is the percent that actually got COVID. Fewer than 1% of them would get COVID. So notice it's a very small probability, which means what's happening is this: if the population proportion of all vaccinated people get COVID is 0.04, when you have a very small percent chance of that happening, you say, well, that must not be true. Any questions on that? I see 50 years. I'm not sure what that was about. Sorry.
Oh, most.
Sorry, I can't hear you. I asked earlier, but don't think you saw. Do we have to use strong or weak in our answers? You don't have to, but you should understand it, and you should know if it's true or not. On the project, you should, because that you have a lot of time to think about it. Most important in 50 years. Oh, I see. Yeah, so maybe most important in 50 years. That actually, that's debatable. Most important in 50 years. There was another big one that before COVID, actually, I used in my example. I don't know what the other really big scientific thing that they did a hypothesis test and they found out it was clear. Worldwide, another worldwide thing. And no. AIDS, no, AIDS, we don't have a vaccination for AIDS, so we didn't even get there. We're still not there with that. No, climate change.
Oh, okay.
So that one's debatable. What's more important? Knowing that we're having climate change or knowing the vaccination worked for AIDS. And I don't think I'm going to go there on what's more important. I'm going to let you think about it because that's not statistics, which is more important, climate change or COVID. That's a whole different thing. But they're both, hopefully, you know, they're both important. Okay, so climate change was a big one, and that's the one I used to use as my key example because that's a biggie. And again, you think of a type 1 and type 2 error, and they're important, right? Type 1 error ends up costing a lot of money when there was no climate change. Type 2 error, you end up doing nothing for climate change, and it destroys the world. Okay. Another one, I think type 2 is worse, but again, it depends on you. If you think money is worse, then that could be worse. Obviously, you know, so it depends. Okay. So then type 1 would be worse, yeah. Because that means you didn't know about climate change, but it happened. Okay, so that's another biggie. So again, one of the things that this is something I love about this class is that I don't have to convince you it's important. There's so many important things that happen that need statistics. And so I can bring up some. Okay. So now let's interpret the level of significance. So I want to do this. If the population proportion of all vaccinated people who get COVID is 0.04 and if. So notice that first part is saying if the null hypothesis is true. And interpreting the level of significance starts exactly the same. If the population proportion of all vaccinated people who get COVID is 4%, and if, actually I can do more, all that is exactly the same. And if another study of 25,000 were vaccinated and COVID tested during and at the end of the testing time, then there would be a 10%, because remember, we're using 10% for our level of significance. There'd be a 10% probability that we would end up falsely concluding that fewer than 4% of all vaccinated people get COVID during these months. And that's what the level of significance is. So one great thing about an online class, everything you do is on the computer, so you can copy and paste that first piece. If I asked you to both interpret the p-value and interpret the level of significance, they start the same, but they end different. Any questions on the level of significance interpretation? So that's the same thing as the probability of a type 1 error. It's repeating what a type 1 error means. Any questions on that? Okay. Just a note, the null hypothesis is what you're trying to refute. The alternative hypothesis is what you're hoping to find evidence that it is true. I want to mention another thing is that if you change the order at which you do things, you're actually being unethical. Okay? Ethics is important. So you should never look at your sample and then based on the sample decide on hypothesis and then find the p-value and then decide whether to reject or not. Okay, that is wrong. You have to have your hypothesis before you look at your sample. Any questions on that? What you can do is look at your sample and then get a hypothesis and then get a new sample and ignore your original sample. That you're allowed to do. But you can't just use your sample to decide on a hypothesis and then use your sample to find the p-value. It has to be a different sample. Does that make sense? So it's very important the order at which you do all this. And I will let you know, I know it's a little early because we're going to be doing this in probably 15 minutes or so. Project 1, you're going to have to do a hypothesis test. You have to do everything in that order, and you should write your paper in that order. Okay, so here's another example. And I don't remember where you're all from. I never say names of people because this is being recorded. Are you both from Tahoe? I don't think one is and one isn't, if I remember right. Yeah. So sorry if you don't know this, but the most important thing in all of Tahoe that we do in science-wise is try to keep our lake clear and beautiful. Okay. If you're not from Tahoe, you've probably been to Tahoe, right? If you've never been to Tahoe, definitely come to Tahoe. You two have been, but those who are watching this, it's a beautiful place. And I've never heard anyone say that's a stupid thing. It's not beautiful at all. It is a beautiful place. So, but if our lake all of a sudden got gross, smelly, and putrid and not blue anymore, all of a sudden it takes away a lot of the beauty of Tahoe. So there is a huge, huge effort in keeping Tahoe blue. So one of the things, and I do this every year as a volunteer, not as a statistician, is they have a, Tahoe blue vodka would be in trouble. It'd be Tahoe gray vodka, I guess. And by the way, the owner of Tahoe blue vodka, I've known him since before he even had it. Good guy. So one of the things that I do every year is they have something called Snapshot Day. Have you done it? The person who lives in Tahoe? Snapshot Day? If not, I recommend it. We go and it's usually in late May. And it's a bunch of volunteers. And we take measurements of kind of chemical measurements of the creeks that are flowing into Tahoe to see if there's issues, and if there's issues, they need to be fixed. One of them, and I just picked one of the measurements we take that most of you probably have heard of before, and that's called the pH. Y'all heard of pH?
Stop it.
Stop it. Okay. Hopefully you've heard of pH. Okay. And we measure the pH of the stream that we're looking at. And there's like a whole bunch of people. Yeah, it's the acidity level. There's a whole bunch of people that volunteer so we can measure most of the creeks that flow into Lake Tahoe. And
Billy, stop.
the idea is that we're hoping the pH is 7 because that's pure water is 7. Okay? What we don't want is the pH to be different from 7, especially far different from 7, which would be really bad.
Shh.
So we're going to have an H naught is now, it's not P anymore. Because what we're measuring is we're not doing a yes or no. We're measuring the pH. And when you measure the pH, you get a number. Okay? Hopefully you get something really close to 7, but you might get 4.2. And that's a disaster, by the way, if you have a pH 4.2 flowing into Lake Tahoe. Or you might get 9.3. That's also a disaster. That's too high a pH. So low is acidic, high is basic. If you didn't know that, that's fine. Okay? So in particular, water soap if it's 4. Okay? It's going to kill all kinds of, it's just bad. Okay? Oh, yeah, water's the other way around. So this is called a two-tailed test. H naught is mu equals 7.0. H1 is mu is not equal to 7.0 because it's bad if it's on either side of 7. Whereas in our last example, we wanted to show that it was less than 4% for those who got COVID. Here, we're hoping this isn't true, but we're going to check to see if it's different from 7. And if we're checking to see if it's different, then it's called a two-tailed test, because either side, left or right, is going to end up rejecting the null hypothesis. Okay? Right, if it was 6.8, it wouldn't be so bad, it turns out, or 7.2. And those will be close enough to 7 that you won't have statistically significant evidence. Do you see that? Because you only have, we didn't have that giant a sample size. Do you see how that works? It turns out there's something called statistically significant and practically significant. Confidence intervals are better for testing practical significance. And that is to say, well, how far away from 7 is it? Confidence intervals can do that. Okay, hypothesis tests measure, is it away from 7? Do you see the difference? So it's very important to understand the effectiveness of a confidence interval versus a hypothesis test. So the confidence interval will tell you how far from 7. The hypothesis test will say, is it not 7? So again, this is a two-tailed test. Here, let's look at type 1 and type 2 error. So type 1 error means we're going to reject H0, accept H1. We're going to accept that the creeks have bad pH that's not equal to 7. Okay. If that happens, what's going to happen is we're going to have this statistically significant evidence. The government is going to fund efforts to mitigate this when it wasn't needed, because the pH was 7 and there were no problems. You see? Okay. That's a bad thing, a total waste of money. Does that make sense? Spend all this money to try and change it, trying to, mitigate the pH issue when there isn't an issue. Okay, that's a type 1 error. Type 2 error means that we weren't able to show that pH differs from 7, but it actually did differ from 7. So now we're not going to get funding to put into mitigation when there's a big problem. And the Tahoe plant and animals will go extinct. Which do you think is worse? A type 1 error or type 2 error? Is it worse to waste money, or is it worse to have an ecological disaster? Okay. I personally think a type 2 is worse, but some people care more about money. Again, I'm not here to tell you what you should think in terms of what's more important, money or ecological problems, but I am here for you to understand the differences. Does that make sense? And if you said that money was so important because if the government's putting money into this, then they're not going to have money for other things and we're going to lose all kinds of other things. That'd be horrible, much worse than, the problem of just losing biological diversity in the Lake Tahoe. I'll accept that. Even though I don't agree with it, I'll accept it for points. Does that make sense? Okay. On the other hand, if you said it's much more important it'd be much worse to have an ecological disaster than to have a financial, mistake, I'll accept that. I accept whatever you say as long as you understand it. Does that make sense? Okay. Doesn't mean I'll accept you as a friend. Just means I'll accept you for points on exams. Does that make sense? Okay, I think a type 2 error is worse, and you did also. And so if type 2 is worse, I'm going to use 0.1 again. Okay, if type 1 was worse, I'd use 0.01. If they were about the same, I'd use 0.05. Okay. All right, now I'm going to tell you what happened. Again, what we had is X bar was 6.4. And S was 3.5. and N is 15. Okay. By the way, is this sample size large enough? Yeah, not really. It's not a great sample size. You should worry a bit about the sample size. That means we must assume the distribution of pH levels is normal, which is probably a terrible assumption. But again, maybe you can only get so many volunteers, or maybe there's only so many creeks to test. Does that make sense? X bar is a sample size. X bar is not a sample size. X bar is a sample mean. N is a sample size. Does that make sense in terms of the notation?
Mhm.
Okay. Sometimes you can't get a bigger sample size because you can only find so many volunteers. Okay. Or maybe logistically you couldn't, test that more than 15 creeks or something like that. Does that make sense? So the number of creeks tested was a sample size. Okay, and in this case, that's what they were able to test that year at least. Okay, so we have to assume, again, it's horrible to have to assume. That means it's not that reliable. I think even though I got a test statistic, I think I'm going to show you how to put this in the calculator because it is important. Testing the creek twice, then you don't have independent events. But what you can do is you can do it over years. And that's a little better. I'm not going to get into the chemistry, but there's some chemistry involved, if that makes some sense. And by the way, my minor was chemistry in college. So I know a little bit. Okay, I'm not an expert in chemistry, but I did have a minor in chemistry. Did take a lot of chemistry classes. Okay, so we're going to do the calculator. Which calculator do you think we're going to use? Let me show you again what we've got. X bar was 6.4, S was 3.5, N was 15. We have our H naught and H1. Mu is equal to 7.0, mu is not equal to 7.0. Which calculator? We're not doing a confidence interval. Remember, we're doing the chapter of hypothesis testing. We have an H naught and H1. We got to test that hypothesis. We don't have data given. So it's not 15. Yeah, it's 14. We have statistics here. So I'm going to click on hypothesis test for a mean with statistics. Do we know the population standard deviation? Okay, no, and that'll almost always be no. I only put this, I didn't used to have this up there, but there were some other professors from other colleges that wanted it, so I put it for them. And then we have our S. S was 3.5. We have our X bar. X bar was 6.4. We have our N, which was 15, with 15. Mu naught, that is the hypothesized mean, which in this case was 7.0 or 7. Does that ring a bell? Any questions on that? Then are we doing a less than, a greater than, or not equal to? So again, that's why we have all this written first, so we can put this in. We have a not equal to. So I click on the not equal to, and hit calculate. The test statistic is negative 0.66. The p-value is about 0.5175. By the way, this is brand new. So if you find mistakes, please let me know. You are the first students ever of my students to ever see the calculator show the picture. So I put the picture in, that was my winter break. I did all the pictures. So, so here's the picture. And it shows the 3 rejection regions, by the way, just in case. You should have seen it yesterday. You didn't see it in the video yesterday, but if you did it by hand, you would have seen it. Yeah, because the video I made a year ago. Okay. Yeah, you're the first class ever to see the picture. So, which means there might be mistakes. All the pictures for the whole class, for all the calculators, basically. I put those in over winter break. Yeah, the colors regions weren't there in the video. But they were there if you used a calculator. Unless you used it in December. Because that's when I made it, or before December. Okay. So our p-value, notice what's the p-value, what's important about this p-value? What's important? Yeah, it's really high, 0.51. That's a really high p-value. Okay. And notice on the picture, it's pretty close to 7 in terms of the graph. It's not very unlikely at all that if the mean is 7, that we'd get a 6.4 for x bar. Okay. Yeah, it's like flipping a coin. It could happen. It's not, you wouldn't say, well, that's weird, right? Because there's like a 52% chance that you're going to have something within that, left and right, by the way. And by the way, left is 6.4. What would the right side be? The symmetric right side be? Because this is always hard for students. So what would the symmetric right-hand side be? Yeah, 7.6. Because 6.4 is 0.6 to the left of 7. So 0.6 to the right of 7 would be 7.6. Any questions on that? All right, so now let's go back. So the conclusion, we have our p-value is 0.52, which is really big. So there is statistically insignificant evidence. Sometimes you'll also see insufficient. Those are the two words you'll see for when you fail to reject. To support the claim that the population mean pH of water that flows into Tahoe differs from 7.0. If you don't have the word population and you don't have the words statistically insignificant evidence, I take off points. Just note, when I highlight something in red, that means you have to have it. And if you're colorblind, statistically insignificant evidence, highlighted. Population, highlighted. Any questions on that? Okay, what does it mean to have a p-value of 0.5175? So let's type this out. That means that if the population proportion of pH in all creeks that flow into Lake Tahoe, sorry, population mean, not proportion, my mistake. pH of all creeks that flow into Lake Tahoe is 7.0. And if we conducted, or if we measured another 15 creeks, then there would be a 52% chance that the sample mean for the new study would either be less than, and then if you remember, our x bar was 6.4, or greater than 7.6. Any questions on that? Okay. I'm going to highlight all the way up to the word A. I'm going to copy it. And we're going to interpret the level of significance. And the reason is I can just paste it. If the population mean pH in all creeks that flow into Lake Tahoe is 7.0, and if we measured another 15 creeks, then there would be okay, now our level of significance was 0.1 or 10%. 10% chance. That's 10% chance that we would end up falsely concluding that the population mean pH of creeks that flow into Lake Tahoe is or just differs from 7.0. Let's try again. Any questions? Any questions on this? Okay. I'm gonna do this one quick. So suppose you want to see if women are not drinking the recommended 2.7 liters per day on average, okay, of fluid. If you don't drink enough fluid, then that's bad for you, right? You get dehydrated, okay? So H naught is mu equals 2.7. H1 is mu is less than 2.7. Okay, so here if you drink too much, usually that's okay. I mean, you don't want to drink 1,000,000 gallons or something, but but if you drink 4 gallons a day, 4 liters a day, that's fine. But if you drink 1 liter a day, that's not okay. Does that make sense? Okay, so we're gonna do a left tail test here. Okay, let's suppose we decided on a 0.1 level of significance. Okay, because again, it's probably worse to not know that women have problems and not help them than to think women have problems and encourage them to drink more when they didn't really need to. So I'm going to let it be 0.01. And here's our data. Okay. When I have the word suppose, all these supposes, do you remember what that means in terms of this data? Yeah, it means I made up the data. This is not a real survey. This is not a real survey. So the pH was actually that was one I actually got because I was part of it. But this is not a real survey, but it could be done. So I'm going to copy this, and now this won't work. So I need a different calculator. Let's go back to the calculator. Which calculator do you think I need to use now? Is it a proportion? Look at our data. 2.4 was the answer to the first survey question, not a proportion. Does that make sense? This is quantitative. It's a bunch of numbers. For proportions, it's yeses and nos. Okay, so which one? Which calculator? One of them. Yeah, hypothesis test for a mean with data, number 15. Okay, because we're looking at a mean, it's quantitative data. We have data, and we're doing a hypothesis test. So I click on that. And then I copied, and I'm going to paste the data in. Okay. It would take a while to type them all in, so I didn't want to bother. And here, we don't know sigma, so leave that blank. Okay, and it does say if the population standard deviation is known, or leave it blank if it's not known. Okay, we do have a lesson. Mu naught in this case, let's take a look. Mu naught was 2.7, because that's the mu equals in the H naught. So 2.7. And hit calculate. Any questions on this? Okay, note, by the way, the important numbers are p-value 0.03. Okay, 0.03 is not less than 0.01. So that means we failed to reject the null hypothesis. I'm not going to type it all out because we don't have much time left. I'm going to say it. We're going to say that there is statistically insignificant evidence to conclude that the population mean number of liters of water that women, or liters per day on average, that women drink is less than 2.7. So it's insignificant. I do want to mention something that's pretty important. If you get, we're using 0.01 and we got 0.03, it's like we're close, but we didn't quite get there. Do you think it would be worth using a larger sample size so that our margin of error could get smaller? Our standard error could get smaller in particular? Or do you think it'd be a waste of time? Yeah, it costs money to do more people, but is it hopeful that you still might be right? Yeah. So we have a 0.03. We weren't able to say we were right? We had insignificant evidence, but it's still worth it to try to do a larger sample size. Yeah, in the last example, when we had over 0.5, it was 0.5 something, 0.52. Then you'd say, it's just time to give up. Okay. You don't say it's time to give up because the null hypothesis is true, but you say, well, there's a good chance that it's true, so I'm not even going to bother. Do you see? Okay. All right, dehydration could be a problem for athletes, by the way. All kinds of health problems could happen if you're dehydrated while you're doing a heavy athletic thing. Just let you know that. And also there's other health issues too. I'm not going to get into medicine though. So dehydration could be a problem. But I'm not going to get into that. This is a stats class. Any questions on that? So when you do the project, for example, which I'm very soon to get into, after looking at your p-value, then I want you to revisit and decide whether dropping the standard error would be worth it. And you drop the standard error by having a larger sample size. Or based on your p-value, maybe it's not worth it. Okay, by the way, had you gotten, let's say 0.02, say 0.001, and you rejected the null hypothesis, kind of like in the first example, is it worth it to do another study? What do you think? If you rejected the null hypothesis, do you do another study with a bigger sample size? And the answer is no. Because you reject the null hypothesis for the vaccination one, you say go for it. Go get back, we're going to approve the vaccination. Do you see? Not you need to do another study. Do you see how that works? Okay. If you don't trust them, then you might want to do another study. But that wouldn't be you. That would be someone else who did the study, and you don't trust their study. But no, if you got it and you reject the null hypothesis, don't do another study. The example I like to give is it's a soccer example. Let's suppose that you're the coach of the soccer team, and at LTCC, that's our main sport here, in terms of we actually have a soccer team. And let's suppose that your team is up 3-2. and your player is 5 seconds left in the game. Your player is about to kick for a goal, and the other team pushes the player, commits a foul, but the ref doesn't necessarily see it. It's filmed maybe. Should you argue? No, you won the game. There's no reason to yell at the referee if you won the game. Does that make sense? Similarly, if your p-value is really small, you don't say, I need to do another study. Okay, on the other hand, what if you were down 9-1 and there's 5 seconds left in the game? Same situation. Do you argue? Yeah, again, no, because you might go home crying because you lost, but you're not going to win. Do you see that? Okay, on the other hand, what if it was a 3-2 game? You were down 3-2. Now do you argue and say, hey, look at the video? Yeah, now you argue. Do you see? So if you lost, but you're close, it's time to try and make the standard error smaller by arguing, in this case, is getting a larger sample size. Does that make sense? Any questions on this idea? Okay, so these are templates, by the way. So if, and I write the null hypothesis is true, don't write the words the null hypothesis is true. You need to write that in. And another sample of however many you did was taken. Then there would be a, whatever probability your p-value was, that, and then the results of the new study would be at least extreme as a result of this study. And again, that needs to be with the results of the study, what they were, and how extreme they were. So the first template was quick. There is statistically the significant or insignificant evidence to support the claim that the population, it'll either be mean and proportion, and then it'll be what your H1 is. Okay. XXX means don't put a bunch of X's, please. That means you're going to put in whatever is relating to what the study was. And then the level of significance, let's go like this, so I can have them on the same, is if the null hypothesis is true, and again, don't put this in, that's like XXX. And another sample, oh, that should be of however many was taken. Then there would be a whatever probability, okay? And by the way, these X's are not the same as these X's. These X's are the p-value X's. These X's are the level of significance X's. That the new study result in falsely concluding that, and then whatever the alternative hypothesis is stating. Okay, I can't get through all these, so I had them just in case, but I can do the secret word. The secret word is population. And if you remember, that was an important word that you had to have when you're writing down the conclusion. Okay. By the way, the conclusion is you reject or fail to reject. Okay, that's different than asking. So if I say state the conclusion, do not state if the null hypothesis is true. That's not the conclusion. Got it? The conclusion is it'll either be statistically or insignificant, or statistically significant or statistically insignificant. Okay? That's how your conclusion starts. Interpret the p-value, interpret the level of significance. Those start with if and then the null hypothesis being true. Okay? By the way, you never conclude that the null hypothesis is true. That never happens. You only say, I don't know if the null hypothesis is true to conclude. Or you say, the alternative hypothesis is true. Never say the null hypothesis is true. Any questions on that? Okay, so now I want to talk about project 2. And now let's go to Canvas. So a few things, project 2. You have almost till the end of this course, March 24th. Do not wait till the end. Okay, you're not quite ready to do the full project yet. That's after next week, you'll be ready. Now is the time to start thinking about the project. Okay, so step by step. What's the first step of project 2? And the hint is it's exactly the same as the first step is project 1. You're asking, what if the p-value is 0.9999? You still can't say the null hypothesis is true. Then you go for confidence intervals. Yeah, your first step is to get partners, or make sure that the partners you had before are still happy to be working with you, and you can keep the same partners if you want to, but you don't have to. And again, strongly recommend 3, because that way if someone leaves, you still have at least 2 of you. Yeah, still quantitative, I'll get into that in a bit. But I wanted to start with the partners, okay? So same rules on the partners. Do not work by yourself. That's a disaster. Got it? You pretty much can't pass if you work by yourself. So make sure you get partners. And 3 is best, 2 is okay. Okay, you are allowed, I posted in the discussion boards a project 2 discussion forum. Use that, not the project 1 discussion forum. Okay, so step 1 is to find partners. Now let's go and click on project 2. And here's what you're going to have to do. Okay. And again, we're not ready to do all this yet because next week we'll get into it, but you can understand the ideas this week. So the purpose of project 2 is to use confidence intervals and hypothesis testing to support or show lack of support for a research project. Got it? Okay. So this project is all about confidence intervals and hypothesis testing. So almost all of your writing should be about that. There's a little bit on other things, but most of it should be on that. Okay. You first have to decide what you're interested in researching, then design your study and collect your data. You are responsible for collecting data, not grabbing someone else's collected data. Okay. It does not have to be a survey question like project 1 was. This is very different than project 1. Project 1, a big part of project 1 was really learning about sampling technique. Whereas in project 2, I really don't care. Okay. You are allowed to use convenience sampling if you want to. You don't have to, but you're allowed to use convenience sampling. I don't take off points for using convenience sampling. As long as you, but be honest, if you use convenience sampling, say you use convenience sampling. Got it? That's all I ask. Like project 1, you have to identify a client who will be making decisions based on your results. Should say based, sorry about the typo. Okay, and next, you're going to analyze the data to see what it tells you and whether it supports your hypothesis. Yes, you can be pricing data from stores, but I do want to mention, this is important, and this is why you're not quite ready yet, is this, unlike project 1, is a comparison study. You're going to comparing 2 means. And that's chapter 10, by the way. So that's why you're not quite ready yet, because that'll be chapter 10. But you're ready to start thinking about it. You're going to compare 2 things. So if you're going to do pricing data from stores, so for example, I have had students look at online shopping versus face-to-face shopping. And they compared, is it cheaper to buy online? Does that make sense? And they went and looked at things that were online and things that were in their local store. Okay, so they didn't have to ask anybody. Yeah, you are allowed to do a survey, but you don't have to you're doing a survey, but you don't have to do a survey where you're asking people. Survey just means you're collecting data, by the way. You don't have to do a survey of asking people. You can survey data. Okay, it has to be quantitative. And I mentioned last week, a big reason for that is that if it's a survey of a yes/no question, do you remember to have pretty good data? Remember how big a survey you need? Remember kind of the standard amount if it's a yes/no question? No, that was to get normal distribution, but to have good data for a reasonable level of significance or, confidence level. And to have a reasonable margin of error. Remember? Yeah, like 1,000. And I'm not trying to be evil. To ask you to ask 1,000 people is not reasonable. Do you agree? So that's why I don't have you do that. Okay. Whereas with a quantitative, you don't need as big a sample to have good data, it turns out. Sound good? All right, the sample sizes must be greater than 30. Okay. It's still, even if you had a YouTube channel, it would take, even to count it would take forever. Okay. Okay. Yeah, so sample sizes must be greater than 30. Notice this is plural. Why did I write sizes instead of size? Yeah, it's a comparison study. So you're comparing two samples. Okay. So they both have to be greater than 30. Okay. So if you were doing the online, like the online shopping versus face-to-face versus in-person shopping, that would mean you'd have to look at more than 30 items, both online and, so not 60, 62 is the minimum, by the way. So both online and in person, and that would be 31 of each. Do you see? Which is 62, by the way, not 60. Okay, any questions on that? Okay, we don't have the math yet to be able to do this because that's chapter 10, but at least I don't think it's that hard to understand what I'm asking, right? Okay, next week I'll show you how to go into the Google Sheets program, which you have to go into. Okay, you're gonna have to use the Google Sheets. I made it for the project. It's not hard to use, I promise you. Okay, but it's very different in terms of what you're focusing on. For the last project, you were focusing on the statistics. You were focusing on, the standard deviation, the mean, the median, the quartiles. You're focusing on the bar, you're focusing on the stem and leaf diagram, the box plot. Remember all that stuff? Histogram. This is not what you're focusing on. You're focusing on the confidence interval and the hypothesis test. Got it? Focus on that. Okay. The only statistic that I do want you to also focus on, because it's very important for the confidence interval and the hypothesis test, the main one is the standard error. It's also our new one. Because if your standard error is too big, then your p-value will probably be large, even though you might have been right in the first place. Do you see? Or if your standard error is too big, then your margin of error is going to be too big, and you're going to have a confidence interval that's worthless. So you're going to have to look at them and decide. Does that make sense? Okay. So the standard error you should be writing about throughout the paper. Yeah, kind of like a sequel to standard deviation. I like that. That's true. Because that's like the standard error is the biggie for sampling. The standard deviation was the biggie when you weren't when you didn't do inferential statistics, when you did descriptive statistics. So that has to do with it. Whereas this project is on inferential statistics. And again, don't ever use the word prove because you won't be able to do that. Okay. If you increase, now the math isn't any easier if you increase your sample size, actually. Even if you had to do it yourself, the math would be harder if you had to do it yourself. If you increase your sample size, what you get is you get more reliable data, not better math. Does that make sense? So you're able to get a confidence interval with maybe a higher confidence level and still a small margin of error. Do you see how that works? The math isn't any easier. You're just putting the data in, letting the spreadsheet do the math for you. And I'll show you that next week, I promise. So that's about it. It's 2:40, which is my, what I always try and end there earlier within a minute or two. But hopefully this all makes sense. And if not, at least those who are here, you can ask me questions after. And I'm gonna stop the recording.